Okay, so moving on to the next graph, which is that of y equals cos x. So notice all we've done is we've changed it from the sine ratio to the cos ratio. Now let's have a look at the characteristics of this particular graph. Let's look at the similarities first of all. We've drawn it from minus 360 to 360 in this example. Again, your teacher can tell you to draw it for any particular interval. Of course, these are also degrees, so when you draw your axes, please make sure that this is your angle axis, all right, and these are your numbered axis. All right, notice that again, if we take a cos curve, if we take it from 0 to 360, can you see that this is its passage through the first quadrant, the second quadrant, what cos does in the third quadrant, and then what it does in the fourth quadrant. And again, it has taken 360 degrees to complete its journey. And if we were to continue, it would continue with an identical journey thereafter. So once again, we can say that this particular function has a period of 360 like the function y equals sine x. Now, we're not going to go to the calculator story again, but obviously, if we went there, we would plot in exactly the same values, and it would give us the values off of the graph. So let's have a look at where that differs. Now, remember, sine started here, but cos, very importantly, at 0 starts at 1. At 90, it comes down to 0. That's in the first quadrant, cos is positive. In the second quadrant, cos is negative. Then at 270, it comes back to 0, and then it peaks again at 360. So what we now have is our maximums at different places than before or compared to the sine graph. So our maximums, if you have a look here, are going to be at 0 with 1, and then 360 degrees previous to that at minus 360 and 1, right? Then we're going to have our minimums or our trough happening. You can see here is where it comes down to an all-time low, which is going to be at 180 degrees with minus 1. And you guessed it, if you come 180 degrees left, takes us to minus 180 degrees with minus 1. So we've got our period is exactly the same as the sine, but we've got different peaks and different troughs. So our minimums and our maximums are different. Right, what else did we have to discuss? We also, of course, have to look at the range. So let's look at our range. And again, our range is our y values that are taken up by the graph. Now you can see that the minimum that the graph ever comes down to is minus 1. So there's no point with a y coordinate being 2 or minus 2 or minus 1.5. All right, and up here the maximum is 1. So there's no y value higher than 1 on this particular graph. So our range again is going to be minus 1 to 1. Exactly the same as the sine graph. And then the only other thing that we've really got to have a look at is going to be our amplitude. And remember how I explained the amplitude before? All right, let's look at our range. Can you see that that graph spans 2 units in total? All right, which means that we have to give half to an up bump and half to a down bump. So our amplitude would also be 1. So let's look at the language again. The period is how many degrees it takes to make a pattern. And remember, our pattern here is starting from 0 up to 360, and then it just repeats itself. Then again, we've got where does it maximize? At 0 and minus 360. Where does it minimize? At 180 and minus 180. Our range is still from minus 1 to 1, and the other language we need is the amplitude. And again, you can see that the amplitude is really just the height of the graph. And you can see that that is Even although that's from 0 to -1, we would say that that distance is 1 positive, and that distance is 1 positive. Right, again I ask you that this is going to be the standard form for every time they ask you to draw y equals cos x. So you need to commit these characteristics to memory. Those are the basic graphs that you need, because moving on now, we're going to actually have what happens if we put a variable in front of a cos graph, a sine graph, etc. So what we need to have a look at is our cos graph is the blue solid graph, starting at 1 all the way across to 360 degrees. All right. However, if we now have a 3 in front of the cos, what is happening there is that it's taking the original graph and multiplying every value by 3. So at 0, it was 1, but 1 times 3 is 3. At 90, it was 0, and 0 times 3 is still 0. Can you see that at -1 was the original graph? If we times that by 3, we land up at -3. And so on. Now, can you see that what has happened here is that the graph has actually stretched? So the only thing that has really been affected is definitely not the period, but can you see that the range has been affected and the amplitude has been affected? So that means that in this particular case, my range would now be y is spanning from -3 up to 3. And my amplitude is therefore also affected. All right, and can you see that that spans 6 units in total? So that actually means that the height of one bump is going to be half of 6, which is 3. Notice that the place that the graph cuts on the x-axis is identical to previously, but the maximums are not at 0.1 anymore, but at 0.3, and not at 361, but at 363. So that is the effect that the number in front of the trig ratio has. What it does is it stretches the graph vertically, and it affects the amplitude. Right, let's see if we can put that knowledge to good use in the next one. So now they come along and they say, right, if we've drawn y equals cos x, the normal solid blue graph, what would the graph of -3 cos x? So in other words, they are asking us to consider the effect of the -3. Remember last time was 3, this time it's -3. So can you see that where it was 0, 1 before, if we take that 1 and times it by that -3 in the front, it takes the value of 0.1 and takes it down to 0 -3. Here it was 0, and it's going to stay 0. Here it was 270, and it's going to stay there. But can you see that 180, where at 180 it was at -1, if we took 180, okay, it was at -1, and that was in our normal cos graph. Now, in our y equals -3 cos x, you can see that you're going to take the -1 and times it, the -1 and times it by -3, and you can see that it sends that point up to 3. So what effect has the -3 had? Let's just remember that the other graph that we drew previously looked something like this. Okay? And you can see that the pink graph is actually just a reflection across the x-axis. So can you see that the yellow point here has actually reflected from 3 down to -3? The 0 has stayed. All right? This point down here at 180 -3 has reflected up. So can you see that the yellow graph, our original 3 cos x, was already a stretch graph, but the effect of the minus is just to reflect it and really turn it upside down. So the 3 stretched it, and the minus actually turned it and flipped it across the x-axis. Now, obviously, if we were putting this into our calculator, it would give us all of these values, but we do need to have an expectation of what characteristic that is going to affect on our graph. And it obviously affects our amplitude, and it affects the graph flipping across the x-axis. Right, on to the next one. Let's have a look if we can think of the normal sine graph. Right, remember that is our blue graph with the characteristics starting at 0, peaking at 90, coming down and troughing at 270 and completing its course by 360. And this particular slide wants us to have a look at the effect of the half. Now it's a positive half, all right? Now what that means, think about it, is it's going to be a half of your original graph. Now can you see that your pink graph, your dotted line coming in here, can you see that all that's happened in relation to the blue graph is that it's taken the blue graph and it's kind of squashed it. It's made it not as humped. So this distance here is only a half, and this distance here is only a half, where previously it spanned 1 unit. So what would the range of this graph be? Well, I'm sure that you're saying it's definitely going to be squatter, and it's going to be from a minimum of minus a half up to a maximum height of a half. Right? What would our amplitude be? And you can see that that question is very easily answered because that spans 1 unit, and each bump is then going to be only a half a unit high. Notice that the period, as before, is 360 degrees. And notice too that the x-cuts, so where the graph actually cuts on the x-axis, stays exactly the same. And the peaks are at the same place, they're not as high. And the trough is at the same place, but not as low. So once again, what is the effect of the half in front of the sine x? Remember when we started off, we said that we were going to have a look at not only y equals sine x, but also y equals a sine x. And in this case, our a is a half. So what effect is that half having? All right, it's actually only affecting the height or the amplitude, and it's definitely affecting the range. But it does not affect it does not affect my period. Notice too that in this case the a is a half, and the a is a positive value. So can you see that everything for the blue graph, as it increases, so will the pink one. As it decreases, so is the pink one decreasing. It's just squatter. It hasn't actually flipped it across the x-axis because our a value is positive. How would you go about drawing the pink graph? Well, you would pick up your calculator and you would actually plot in the values, and you would get your function up, and you would put in a half sine x like we did previously. Okay, so bearing that in mind, let's go to the example which is on the bottom of page 119, and let's see if we can put everything that we've done so far into practice. This is, of course, how you would most likely get it asked in a test. Draw the graph of y equals negative a half sine x, and they tell you that they want you to work between minus 360 and 360. So they haven't changed our interval for which they want us to draw the graph. So, of course, guys, you get out your ruler and you make sure that you draw yourself a really good scaled diagram, making sure that you work perhaps with centimeters across and perhaps lines up, and make sure that you label x-axis, y-axis. Because normally in a marking grid, I normally award 1 mark for set out and making sure that you are drawing to scale. Right, remember that we are going to be drawing y equals negative a half sine x. Now, of course, we can go to our calculator, and I'll show you how to do that in a minute. But bearing in mind what we've done so far, we know that a sine graph has got a certain pattern or characteristic. It's got to start at 0, all right? Normally it peaks at 90, comes down at 180, troughs at 270, and comes down at 360. So we definitely know that these are going to be our x cuts, or where it cuts on the x-axis. This number in front here is a half, which tells us that our graph has actually got to be squat. Okay, it's got to be flattened a bit. But this minus tells us that the graph actually has to reflect across the x-axis. So where instead of coming to a half here, all right, it's actually going to come down to minus a half. And instead of coming to minus a half, it's going to go up to a half. So we suspect, without the use of our calculator, that that's what our graph is going to do. And of course, it's going to repeat that same trend on the other side. Notice period being 360, amplitude being a half, range being minus a half to a half. All right, so let's bring up the calculator just to make sure that you do have that capacity to be able to do it on your calculator. So let's go through it again. Remember, you need to set it up and give yourself the table. So f of x is equal to, I want a negative. I'm going to use my fraction button so that I've got my half. And then I'm going to go sine. And of course, I need to bring in my variable. So I go alpha x. Close it off, equals. I need to tell it where to start. So I'm going to tell it to start at 360. I'm going to tell it to end at 360, and I'm going to again go in steps of 90. Right, so looking at the picture, we've got minus 360 should match with 0. Okay? We've got minus 270 should be paired off with negative a half. We've got minus 180 should be paired off with 0. And you can see that I'm doing okay because my values are all the same. Minus 90 with a half, 0 with 0, and so on. And so we would get exactly the same picture had we used our calculator to draw the graph. Now, often they ask us to draw the graph and then to do certain characteristics from there on. So they might ask us what is the period, and of course we can turn around and say the period again is 360, and they might ask us the amplitude. And we're going to turn around and say, well, our amplitude is just the height of a bump, which is a half. And the other common question they ask us is the range. And, of course, the range is going to be from minus a half to a half. And please, guys, make sure that when you do your range, you always list it from smallest value, all right, semicolon, up to largest value. If you do it the other way around, we would mark it wrong. So range always goes from the lowest point that the graph reaches up to the highest point. The other question that they might just ask you is to say from your graph, all right, they might ask you to say, of course, our graph, this is it. So from our graph, they might ask us to solve when is negative a half sine x equal to 0? Now, all that they are actually asking you to do is to have a look at your graph and tell them when the graph takes a y value of 0. And you can see that your graph is going to take a y value of 0 at minus 360, at minus 180, 0, 180, and 360. So you would say x would be an element of the set minus 360, minus 180, 0, 180, and 360. Okay, so once you've drawn your graph, often they then ask you to interpret it as well. Okay, so taking those values off of the calculator, we would fill in our grid. And of course, at minus 360, it indicated that the graph should be at 0. At minus 270, it should have been at negative a half. At minus 180, back to naught. At minus 90, a half. And you can pick up the pattern. It's going to be a 0 again, and then a minus a half, and then a 0, a positive a half, and back to a 0. And of course we can confirm that that's exactly the same as we got when we drew the graph just using our basic knowledge of the characteristics.